Welcome back. The topic of this video is motion management. This is a very important topic in radiation oncology because, as you recall from the previous videos, we can control very precisely where a radiation beam goes in space, but we need to control also where the patient is in the anatomy of that patient under that beam in order to achieve what we want to achieve. So there are many various aspects of this. We'll look at ways to stop the beam, so to arrest it during treatment and to control motion, both during treatment and between treatments, and look at the effects of breathing and so on. So here we go. To understand motion management, let's begin with this view of the position of the patient over the course of many treatment fractions. We saw this in the last video on IGRT. If I zoom in here, you can see that the position of the patient is slightly different from day to day, from fraction to fraction. We would call this kind of variability interfraction motion. So that's variability between treatment fractions. If it were possible to zoom in even closer on one of these individual fractions, I would see within the fraction itself, there's motion as well. That's called intrafractional motion, motion during the treatment fraction itself. Now, some of this can be reduced or managed with the use of IGRT, as we saw in the last video. But regardless of whether IGRT is being used or not, it's very important to have good patient immobilization. This is accomplished with the help of a variety of type of devices. The goal here is not to keep the patient completely immobile, but to make a reproducible setup that's comfortable for the patient. A lot of different devices are used here, and they can be simple. For example, this leg roll under the patient's legs, always at the same position every day. The hand holder at the side of the couch so the patient's arm is in the same position every day. There are, for example, moldable head holders that can go under the patient's head. There are these vacuum sealable bags that mold to the patient underneath to get the same exact shape of the body contour. Because this is such an important issue, a wide variety of devices have been developed, and it's beyond the scope of what I can lay out here to describe them in detail, but it's probably worth mentioning the Aquaplast material. That's a thin thermoplastic material which you heat up and then molds to the patient. When it cools off, it solidifies into a semi-rigid shape. You can see there's holes here, and that's to prevent the extra bolusing effect in the beam. This material can be used in creative ways to achieve the immobilization that you need. Part of the reason I'm mentioning this so much is that it's important when you go to treatment, even with the use of image guidance, you can't completely control the position of everything. You'll see here the patient's neck is flexing a bit, and so if you align one part of the anatomy, another part will be misaligned, even if you have very good image registration. Another simple technology worth mentioning is table indexing. You can see in this image that there's a marker on the table, and the device plugs into that marker. And so if the device is in the same position on the table every day, meaning the patient is in the same position, then that table should also be at a position. And then can be an electronic interlock on that, so you know that if you're outside that position by some tolerance window, then the treatment can be, an interlock can be thrown. That's called table indexing. It's an important safety feature and a way to reduce interfraction variability. All right, so those are some of the issues around interfraction variability between fractions. There are others. This wasn't an exhaustive discussion. For example, bladder filling in a prostate cancer treatment. You'd like to have the same bladder volume each time to better control the position of the prostate or the seminal vesicles. Many issues that can be talked about. But let me jump now to intrafraction variability. So variability and motion that happens on a shorter time scale during a treatment fraction. And again, there's varieties of this, but I'm going to focus the rest of this discussion specifically on respiratory motion because that is very important to understand. I'm going to start with reference to this important document, AAPM Task Group number 76, published in 2006 by some of the pioneering leaders in this area. It's a really good resource. It describes very well the issues around respiratory motion in the context of radiation oncology treatments. The issues here are that as a patient is being treated, the tumors move, both in the lung and also other areas of the body, and that needs to be accounted for. If it's not accounted for, that can affect local control and potentially beyond. And if it is accounted for properly, then you can potentially reduce the margins for treatment. So let's walk through what this looks like and some of the concepts. So the goal here, if I can simplify it, is to first measure the respiratory motion. Let's look at what we're dealing with. Second, to manage it in some way for the purposes of treatment. That could be an active management system, and we'll talk about those a little later. Or at the very least, to account for it in some way in planning the treatment. So let's start with this first part of the goal, to measure the respiratory motion. There are a couple ways to do that. A simple way would just be with fluoroscopy. So that's just taking planar images, movie images from one direction, or potentially two directions, and looking at the motion of the tumor. That's not great for soft tissue visualization, and it can't really be used in treatment planning directly. So the second method is called 4D CT, four-dimensional computed tomography. Let me go through how that works. I was involved in the early development of this, so I can kind of share from that perspective. This is actually the first paper that was written about 4D CT. This is something I was involved with as a resident at Memorial Sloan Kettering with my colleagues. And we didn't, in this paper, you won't see the word 4D CT used because that word was invented only a year or so later by other people. But these are the exact same concepts, and it was kind of an outgrowth of what was being done with cardiac measurements in four-dimensional space. So let me walk through how this is done, starting first with the acquisition of the 4D CT scan. So you start with some way of measuring respiration. In this system I'm showing here, you have a camera mounted on the CT couch that's viewing a block that's placed on the abdomen of the patient, and there's infrared markers in that block, and the camera tracks those markers as the patient breathes. So they go up and down, and here you see the breathing trace. You have going into inspiration, breathing in, and then expiration, breathing out, sort of a long period, and then repeats over and over through the breathing cycle. Then these are reconstructed into a 4D CT image. This can be done in spiral mode. That's the mode that we first reported on. And this works by the CT scanner is acquiring its spiral CT as the breathing happens. And then you can reconstruct CT slices at any point along the spiral. And that is correlated with the breathing trace. So you can go and select whatever phase you want. Let's say we want to make a reconstruction here. Everything at this breathing phase, that just as you're going into the end of expiration. So you select all those slices that correspond to that phase, assemble them, and that's one phase of the 4D CT scan. So it's simple in concept. The other way to do this is in axial mode, where you park the scanner at a particular couch position, let the rotation run, and let the patient breathe as you run, and then go to the next slice, and so on. There are certain trade-offs in spiral mode in terms of the slice thickness and then the distance that the couch travels per breathing cycle. And so that is dependent on the pitch, the slice thickness, and the rotation period of the scanner and the breathing cycle. And here are some of the equations. I won't go into this in detail, but there's some trade-off here. And basically, you can get a lot of gain from running at a small pitch because the distance that the couch travels then is relatively small per unit time. The trade-off being higher dose to the patient. So this might be of interest then. This is the first 40 CT movie ever shown. We showed this at the 2002 AAPM meeting in Montreal. You'll see the image quality is not great, and there's not a lot of anatomy here because we were working with a single slice scanner, but you can see the diaphragm move around. A couple things to note here. When you're looking at 4D CTs, you look at this repeat movie loop. It looks like you're seeing many cycles of the patient breathing, but it's acquired really only over one breathing cycle of the patient, and it's just put into a loop and played over and over. So if there's any irregularity in the patient breathing, that's not really going to be captured. You're only looking at one cycle, so it's kind of a snapshot in time. Now, the quality of these images improved rapidly over time with multi-slice scanners, and now it's regularly used. Here's a tumor that doesn't move very much, but actually people have studied thousands of these things, and it's not easy to predict, so you really need to do the patient-specific measurement. Here's one where it's moving quite a bit in the AP and the lateral direction, but not very much sup-inf. That's unusual. Most tumors move mostly in the sup-inf direction, and then less in the APPA direction, and even less in the right-left direction. But this and other examples like it show that it's important to do patient-specific measurements of this. This technology can be applied beyond the lung. People quickly realize that the abdominal contents move a lot too. And here's an example of the kidneys moving around with respiration, the liver, everything in the abdominal cavity, even down into the pelvis, really. Now let me freeze this movie for a minute and talk about something. You'll see here there's an artifact. You see the kind of strip of the diaphragm that shows up disconnected from the diaphragm. Those are sometimes seen in 4D CT. There are studies of these that are relatively common. It's something to be aware of. It's basically usually because of irregular breathing and catching things outside of the breathing cycle as normal. And there are not good ways to correct for that. And so it's something to be aware of. So now we have a measurement of respiration, and I want to move on and ask the question of how we can manage respiratory motion during treatment. So there are different approaches, and I'm going to walk through them. The first is simple, just margin definition. I'll go through what that means. The second is respiratory gating, and the third is using a breath hold technique during treatment. So looking first at margin definition, you'll recall these definitions of the different volumes with reference to ICRU reports. These were in video 13.1. So we're going to focus in on this, and in particular looking at the GTV. But now we know that in some cases this GTV is moving around. So let's build that into our margin definitions. So this is how this might look schematically. You have this GTV, it moves around with respiration. Now I can capture that shape at a particular breathing phase. I load it in from the 4D CT. And then the tumor moves around, and I capture another phase down here, let's say, moves around some more, and I can capture other phases. So I can get as many phases as I want. And they all get loaded in, and then in the end, what I do then is draw a volume that's going to encompass all of them. This is often called the IGTV, the internal GTV, accounting for motion. So when I have that volume then, all the possible positions of the tumor should lie within that envelope, and so I know that this captures the full extent of the GTV. There are other ways to do this, or other kind of more sophisticated algorithms, but this is the kind of the simplistic way of doing it that's going to capture the most extent of tumor motion. Another approach for respiratory motion management is called respiratory gating. Let me show how this works. Going back to this system to track respiration. I'm showing it on the CT scanner, but this would really be done on the treatment machine. So again, you have a marker block that's on the abdomen of the patient, and this camera system can track it moving up and down. There are other ways to do the tracking, by the way. You could have a pressure belt around the patient or other things. But in any case, you get a breathing trace, goes up and down, and then you have kind of a cycle, a signal that's sent to the machine, a square wave here, trigger signal. So that means that the beam is only going to be turned on during this particular time window. That's the gate. And here we're gating at end expiration. So when the patient comes into this phase, the trigger signal is sent to the machine turns on, it treats, and then it stops at this phase. Goes to the next breathing cycle, turns on again, and turns off, and so on. So there are a couple of drawbacks to this. One, you lose some efficiency because the beam isn't always on. The duty cycle is called, could be 50% or lower easily. Two, if there's any irregularities in the breathing, that's going to turn into an uncertainty or mispositioning of the tumor during the gate on windows. So these need to be thought about very carefully. This is a very tricky system. Then finally, we can ask the patient to hold their breath during treatment. Of course, you have to scan with the breath hold that I'm showing here. And there are many technologies to accomplish this. Here, the one I'm showing has a tube in a patient mouth, and you can measure the respiration pattern. So here's what that looks like. You can see the patient breathing, and then they go into a breath hold. And that sends a signal to the machine that turns the machine on. And the idea is they hold the breath at the same volume every time. This is a closer look at some of the technology for this system. You have the mouthpiece on the right there and the hose that goes into this spirometer device and a nose clip. All of the things that go in the patient mouth are sterile and they're new for each patient. This is the spirometer device. It has a little sort of a fan blade in it, and it spins as the patient breathes, and the spin rate tells you how much air is coming out. And then it's got a balloon valve in it that closes when you want the breath to be held, so it's active assist in the breath hold. Here is showing that you can set the parameters. So you can set the threshold where the trigger starts. This is 2 liters. You can set how long the breath hold lasts, 20 seconds here. And the patient has control over all this. You can see they can hold a button to release everything if they need to. And they're coached through this whole process. The coaching is really crucial to try to get them to the same inspiration level each time. This system is very tricky to use, just like gating. Here you can see the breath hold happening. You can also hold the breaths at end expiration as well. Final technology is compression. So that is very simple. It might just consist of a device pressed, for instance, here against the patient's abdomen, and that limits the respiratory motion, or at least reminds the patient not to breathe deeply. And there's some value in having this in terms of reducing motion, and there have been quite a few studies on this. All right, I hope that gave you a good overview of the topic of motion between treatments and during treatments. It's a very deep and important subject, and so there's lots of reading material, and I'll leave you with some of that here. You can go and dig deeper if you'd like. And then I will see you in the next video. Thank you.